Welcome to the lecture on complex analysis, probability and statistical methods. In my previous lecture, I discussed about the orthogonal property of the complex variable. So in this lecture, I am going to discuss about the harmonic property of the complex variable. So first we will see what is meant by harmonic function. So later I am going to prove the harmonic property of the complex variable. A function pi is said to be harmonic function if it is satisfy the Laplace equation del square pi is equal to 0. So then we can say the function pi is a harmonic function. In the Cartesian form, we will be having dou square pi by dou x square plus dou square pi by dou y square is equal to 0. So in the Cartesian form, to show the function pi is harmonic, we must have the condition like dou square pi by dou x square plus dou square pi by dou y square is equal to 0. In the polar form, we must satisfy the condition dou square pi by dou r square plus 1 by r dou pi by dou r plus 1 by r square dou square pi by dou theta square is equal to 0. So then only we can conclude that the function pi is harmonic in the Cartesian form as well as in the polar form also. So statement: the real and imaginary part of an analytical function are harmonic. So first I am going to prove in terms of Cartesian form. So let me consider the function complex variable function f of z is equal to u plus ivb analytic. So we shall show that u and v satisfy the Laplace equation. It means what? We have to show that dou square u by dou x square plus dou square u by dou y square is equal to 0 and dou square v by dou x square plus dou square v by dou y square is equal to 0 we have to prove in case of Cartesian form. So let me see how to find that. So since f of z is analytic, obviously we will have the CR equations also. The CR equations are dou u by dou x is equal to dou v by dou y. Call this one as equation number 1. One more is dou v by dou x is equal to minus dou u by dou y. Call it as equation number 2. I am going to differentiate equation number 1 with respect to x and equation number 2 with respect to y partially. So we will see after differentiating what we will get it. So on differentiating equation number 1 with respect to x, I will get dou square u by dou x square is equal to dou square v by dou x into dou y, and differentiating equation number 2 with respect to y, I will be getting dou square v by dou y dou x is equal to minus dou square u by dou y square. From the properties of partial derivatives, we have the property like dou square v by dou x dou y is equal to dou square v by dou y dou x. So if these two are same, I can equate these two equations. So I'll be equating what now? Dou square u by dou x square will be equal to minus dou square u by dou y square. I can write like dou square u by dou x square plus dou square u by dou y square is equal to 0. So this is a condition for to show that u is a harmonic. Next, again I am going to differentiate equation number 1 with respect to y now, equation number 2 with respect to x partially. So what I will get it? I will get dou square u by dou y dou x is equal to dou square v by dou y square, comma, dou square v by dou x square is equal to minus dou square u by dou x dou y. So since from the partial derivatives property, we have dou square u by dou y dou x will be always equal to dou square u by dou x dou y. So since these two are same, again I can equate these two equations. I'll be getting what? Dou square v by dou y square is equal to minus dou square v by dou x square. So it will be equal to what? Dou square v by dou x square plus dou square v by dou y square is equal to 0. I got it. So hence I can conclude what? V is an harmonic property. So since I got both u and v are harmonic, so in the case of Cartesian form, I can conclude that both the real and imaginary part of an complex variable are harmonic here. So now I am moving on to the polar form. So in the polar form, let me consider the function f of z is equal to u plus ivb analytic. So now we shall show that u and v must satisfy the Laplacian equation. That is, this u and v must satisfy this equation dou square pi by dou r square plus 1 by r dou pi by dou r plus 1 by r square dou square pi by dou theta square is equal to 0. So since here f of z is analytic, we must have the CR equation in terms of polar form also. It is given by what? Or dou u by dou r is equal to dou v by dou theta. Call this one as equation number 1. And r dou v by dou r is equal to minus dou u by dou theta. Call it as equation number 2. So now what I will do means I am going to differentiate equation number 1 with respect to r, equation number 2 with respect to theta partially. So what I will get, differentiating 1 with respect to r, I will be getting what, r dou square u by dou r square plus dou u by dou r is equal to dou square v by dou r into dou theta, and differentiating equation number 2 with respect to theta, I will be getting r dou square v by dou theta dou r is equal to minus dou square u by dou theta square. So same partial derivative property I am going to use here also. That is, we have the property like dou square v by dou r dou theta will be equal to dou square v by dou theta dou r. So since these two are same, in the place of this equation I can replace minus 1 by r into dou square by dou theta square from this equation. So I'll be getting what now, r dou square u by dou r square plus dou u by dou r is equal to minus 1 by r dou square u by dou theta square. So dividing this equation entirely, I'll be getting dou square u by dou r square plus 1 by r dou u by dou r plus 1 by r square dou square u by dou theta square is equal to 0. So this is the required condition to show that u is a harmonic. So hence I can conclude here u is harmonic. Similarly, again, I am going to differentiate equation number 1 with respect to theta, equation number 2 with respect to r now. So I am going to differentiate this partially. So I will be getting what? Differentiating 1 with respect to theta, I will be getting r dou square u by dou theta dou r is equal to dou square v by dou theta square, and r into dou square v by dou r square plus dou v by dou r is equal to minus dou square u by dou r dou theta. But the property of the partial derivatives, we have dou square u by dou theta dou r will be equal to what? Dou square u by dou r into dou theta. So now I can replace in the place of, in this equation, in the place of dou square u by dou r theta, I can replace it as dou square v by dou theta square. So I'll be getting what now? 1 by r dou square v by dou theta square is equal to minus of r dou square v by dou r square plus dou v by dou r, I will get it. So now on simplifying this equation, and I'm going to divide the entire equation with the r. So I'll be getting dou square v by dou r square plus 1 by r dou v by dou r plus 1 by r square dou square v by dou theta square is equal to 0. This is a required condition to show that v is a harmonic. So what I can conclude here, in the polar form also the u and v are harmonic, I got it. So finally I can conclude that the real and v of the complex variable, that is u and v of the complex variables, will be harmonic, and also in the Cartesian form as well as in the polar form. So in the next lectures I am going to discuss few more examples related to the harmonic property and the orthogonal property. Thank you.